Hello, my name is Korn. Today we will be discussing the topic of biomechanics. Now, what is biomechanics? Biomechanics is the study of mechanics and dynamics of human movement, which combines the principle from physics and engineering to analyze the movement of the human body. The two movements we will be discussing today are lever and torque. First off, what is torque? Torque is, to put simply, a measurement of force used to rotate something around a rotational point. The best example of this is a wrench rotating a nut or a bolt. And the formula for torque is torque equals to length multiplied by force. Now, what is a lever? Lever is a machine that when an input force is acted upon, the output force will be multiplied. Now, the multiplication of force is called a mechanical advantage. There are three types of levers. First class is where the fulcrum or the pivot is in between the input force and the load. The second class is where the load is in between the fulcrum and the input force. Third class is where the input force is in between the load and the fulcrum. The formula for lever is input force multiplied by the length of lever arm for force equals to the load multiplied to the length of lever arm for load. How does these two movements correlate with biomechanics? In biomechanics, torque is often associated with the rotational forces acting on joints, muscles, or objects, influencing movement, where the limbs represent length and the bone joints representing the axis or rotational point. The same concept applies to the lever, where our joints are the fulcrum and the limbs represent length of both sides, and the weights of certain limbs are the loads. The experiment we will be conducting is two people with different limb measurements performing two exercises that involves lever and torque. The two exercises are biceps curls and squats. Our hypothesis is that the person with longer limbs will be able to lift heavier weights. Here's the theory or word problem. A man loads a barbell with 114 kilograms plates. His calves are 38 centimeters in length. His calves are making a 45-degree angle with the wall behind him. If the barbell is aligned with his hip, what is the torque applied to his hips? First, we must find the length of the quads, because that is the limb that is attached to the hip. Thus, we can find this from the trigonometric function sine, and sine equals to opposite side divided by the hypotenuse. Now we know the degree is 45 degrees, so sine 45 equals to the length of quads divided by 0.38, or the length of the calves. Now we get the length of the quads, which is 0.27 meters. Now that we know the length of the quads, we can plug it into the equation. Thus, torque equals to 114 kilograms multiplied by the gravitational acceleration multiplied by the length of the quads. Thus, we get 301.644 newtons. As we see, if we input a longer limb measurement, let's say 0.30 meters for the quads, into the equation, we get the torque force, which is increased into 335 newtons, thus supporting our hypothesis. Another example is of a bicep curls. A man is doing bicep curl using dumbbells. The dumbbells are 16 kilograms. The distance from his hand to the elbow is 30 centimeters. The insertion of bicep muscles to the load is 26 centimeters. What is the amount of force exerted to curl the dumbbell? In this question, the fulcrum can be seen as the elbow, and the lever of force is from the insertion of bicep muscle to the elbow, and the lever for the load is from the hand to the elbow. Thus, we can use the equation input force multiplied by lever arm for force equals load multiplied by lever arm for load. The input force we do not know, multiplied by 0.26 meters, that is the lever arm for force, multiplied by the load, 16 kilograms, multiplied by the acceleration of gravitation, and 0.30, that is the lever arm for load. Now we get the input force, which is 180.92 newtons. Again, if we put in a new measurement, which is a longer limb for this man, we will get a more input force, which is 209 newtons. This again supports our hypothesis that the longer the limb, the heavier the load can get. Now that we are done with the theoretical part of this experiment, we can now go to the real-life results. Now, again, the exercise we will be conducting is squat for the torque movement and bicep curls for the lever movements. The result of the squat experiment is that the load equals to 25 kg, amounting to 245 newtons going downward. My quad measurement is 48 centimeters in length, while Panatat's quad measurement is 53 centimeters in length. In theory, again, the force I was able to output was 253.2 newtons, while Panatat's output force amounts to 259.7 newton, which is more than mine. And the result also supports our hypothesis that longer limbs means we can lift heavier loads, which the result is I was unable to squat 25 kg, while Panatat was able to, thus supporting our hypothesis. For the bicep curl experiment, however, the load is 16 kilograms, amounting to 156.8 newtons going downward. My measurement is lever for force equals to 27 centimeters, and the lever for load is 30 centimeters. Panatat's measurement is 30 centimeters for lever for force and 32 centimeters for lever for load. The theory goes against our hypothesis, where my limbs are a lot smaller, but I was able to amount to more force, while Panatat's measurement, although his limbs are longer, he was unable to output as much force as I can, which the result of this experiment also supports this theory, that although with longer limbs it does not result in being able to lift heavier loads. Now, why is that? Well, for the conclusion of this experiment is that although the longer limbs can help carry heavier loads, but it does not directly influence the amount of load being able to carry. There are more factors that leads to this, such as training regimen and diet and the muscle mass.